So in this video we're going to go over matrix inverses. And so the big idea is to recall from a multiplication of real numbers. When we're working with real numbers, we have a multiplicative identity. And we reviewed this in a previous video. So we have a multiplicative identity. And the multiplicative identity for real numbers is 1. 1 is the number such that when you multiply it by any other real number, you preserve the identity of the real number that you've multiplied. And multiplicative inverses are defined like this. So if I have the number 1/6, we say that 6 is the multiplicative inverse of 6 because when we multiply 1/6 times 6, which is the same as multiplying 6 times 1/6, the product of these two real numbers equals 1, the multiplicative identity. So we call 1/6 and 6 inverses of each other, or multiplicative inverses of each other. So we're going to do something similar with matrices. And what we want to recall is for a square n by n matrix, we defined the multiplicative identity matrix, which we called I sub n, to denote that it's for an n by n square matrix. We identified that the multiplicative identity matrix, which plays the role of the number 1 for matrices, is just a n by n diagonal matrix for which the diagonal elements are all 1s. And so then for matrices, we do something similar to what we do for real numbers. We say, hey, if we have a square matrix A, it's a square matrix, so it must be a square matrix. If we have a second matrix B, and it is the case that A times B equals B times A equals the identity matrix, which plays the role of 1 for matrices, then we say that A and B are inverses of each other, or B is the inverse of A. And then we use the common notation for inverses, which is to put a -1 kind of in this exponent position. But we want to recognize that -1 in this case isn't being used as an exponent when we are using the -1 in this context. It is identifying that this is A inverse. So we read this as A inverse. So that's the big idea. We want to find a matrix B, or A inverse, such that when we multiply A times the inverse of A, or A inverse times A, we get the identity matrix for the appropriate square matrix that we're working with. So in this case it says, show that for A equals the 2 by 2 square matrix 1, 2, 3, 4, that its inverse is -2, 1, 3/2, -1. So to verify that this matrix is the inverse of A, what we need to do is take the product of the two matrices and verify that we get the identity matrix. So first we'll do A times the matrix that is A inverse. So -2, 1, 3/2, and -1/2. So we take the product, and so we have a 2 by 2 matrix times a 2 by 2 matrix, so we're expecting a 2 by 2 matrix as a result. So we take the row 1 and dot it with column 1, so we get net 1 times -2 is -2, plus 2 times 3/2 is 2, so we get -2 plus 3. We get a -2 plus 3 there, and in the next position we get 1 times 1 is 1, plus 2 times -1/2. So 2 times -1/2 is -1. And I'll get rid of this mess so it's not messing me up. And then we go row 2 times, or dotted with, column 1. So 3 times -2 is -6. Plus 4 times 3/2 is going to be +6. And then we get 3 times 1 is 3. Plus 4 times -1/2 is -2. And then we simplify the entries, and we get -2 plus 3 is 1, 1 plus -1 is 0, -6 plus 6 is 0, and 3 minus 2 is 1. So we get the 2 by 2 identity matrix, or I sub 2, which is the notation for the 2 by 2 identity matrix. And because matrix multiplication isn't commutative, you also need to do the product the other direction. You need to take the negative 2, 1, 3 halves, negative 1 half, and multiply it by A. If you're asked to verify that one matrix is the inverse of the other and you don't do the product in both directions, that would be something that would cause you to lose points on that particular problem. So 2 by 2 matrix times a 2 by 2 matrix is going to generate a 2 by 2 matrix. The dot product of row 1 with column 1, so we get negative 2 times 1 is negative 2, plus 1 times 3 is 3. Row 1 dotted with column 2, we get negative 2 times 2 is negative 4, plus 1 times 4 is 4. 3 halves times 1 is 3 halves, plus, and then we get negative 1 half times 3 is negative 3 halves. And then row 2 dotted with column 2, 3 halves times 2 is 3, plus negative 1 half times 4 is negative 2. And then we simplify. Negative 2 plus 3 is 1, negative 4 plus 4 is 0. 3 halves plus negative 3 halves is 0, and 3 minus 2 is 1. And again, we got the 2 by 2 identity matrix. So this verifies that A and A inverse are A and A inverse are actually inverses of each other. So again, the big idea is we have an identity element I, which is the identity matrix, and we need to show that the product of matrices equals I if we're going to verify that we have matrix inverses, or multiplicative matrix inverses.